Thank you, Ava, for that kind introduction. And thanks also, Yuval, for providing some context for the prize. Thanks to the committee for bestowing this honor on me, but most of all, I want to thank my collaborators, without whom these contributions would just not have been made. Differential privacy, no doubt, contributed to the fact that I'm giving this lecture, and I'm not going to talk about differential privacy today. However, tomorrow's opening plenary lecture is on a beautiful and very beautifully written paper of Mark Bunn, Roy Livney, and Shai Moran on the equivalence between differentially private classification and online prediction. So in today's talk, I want to pull together threads from 4 different areas: statistics, complexity theory, algorithmic fairness, and law. And with that, I want to share my screen. Great. Okay. In her prescient 1979 article, Barbara Underwood, now the Solicitor General for the state of New York and then a professor at Yale Law School, discussed the use of individualized or clinical decision-making versus the use of statistical inference in what she describes as 2 different ways of approaching the task of moving from evidence to facts, pointing out that the task presents similar problems whether the facts to be found are past or future. So as much as we hear now about algorithmic methods for release and detain decisions, we can also foresee their contribution to decisions of guilt and innocence. Algorithmic predictors are increasingly being used to score individuals. And as Underwood notes in the opening lines of this abstract, important benefits and burdens are distributed in society on the basis of these predictions, including release from prison, placement in schools, jobs, and the granting of retail credit. My work in this is driven by a practical question. If I am asked to testify about the meaning of algorithmically derived risk scores, what will I tell the court? Or maybe the question will come up in the context of a congressional hearing, or even in a meeting with congressional staffers who are trying to write useful and meaningful legislation. I really believe that as technologists, we have a responsibility to inform officials of the consequences of the decisions and the choices that they are making, that they have been elected to make. So with that backdrop, let's explore the question of what these algorithms are trying to do. So risk predictors assign probabilities to individual instances. What is the probability that it will rain tomorrow? What is the probability that individual X will repay the loan? What's the probability that this tumor will metastasize? What's the probability that Y will commit a violent crime, say in the next 2 years? These numbers can have life-altering consequences. Will the loan be granted or declined? Should the patient choose surgery or chemotherapy? Should the defendant be detained? Should the prisoner be granted parole? The problem is, what is the meaning of the probability of a non-repeatable event? It's not as if we can give X the loan, see what happens, rewind history, give X the loan again, see what happens, rewind history, and so on, and derive from this a probability or a fraction of instances in which X repaid the loan. So in other words, what is it that the algorithm is trying to estimate? So one interpretation of a risk score is the fraction of positive outcomes among people like X, or days like today, or tumors like this one. And indeed, when the representations of individuals is coarse, we have collisions, and these lead naturally to probabilities. people with the same covariates as you, or whose tumors had the same genetic markers as yours in certain locations. Let's say, have a 40% chance of 5-year survival, or 70% chance of 5-year survival with this course of treatment. So that could be obtained, for example, from a study of tumors that look in certain locations in the genome, the same as this particular tumor. And we look at the fraction of those that look the same as this one in these pink locations considered in the study. We look at the fraction of those that have metastasized. But maybe there's another study which looked at other locations in the DNA, and in the tumors that looked like this one in these other locations, 40% of those metastasize. So as this example makes clear, representation is crucial, and representation can also be a vector of bias in decision-making algorithms. So the choices as to which fields or which covariates should be selected that are made by the data gatherers and the algorithm designers are a vector for bias. Now, when the representations are rich, we don't expect to have these collisions. We don't expect that two individuals would be identical. And that's going to be the scenario that I'm going to talk about in the remainder of this lecture. So we're going to assume that we have a distribution in an instance space, which is individuals together with outcomes. In this talk, these are binary outcomes, but they could be arbitrary. So the algorithm doesn't see the whole person. Even if it gets your entire DNA sequence, you are more than your DNA sequence. Nonetheless, the algorithm operates on some feature space, and so there's some kind of a representation mapping that maps individuals from real life to their representations, and that's what the algorithm gets to work on. And again, in this talk, the representations are going to be very rich, and we do not expect, we're assuming that there are going to be no collisions. So we're going to use a common mathematical model that there is somehow a notion of an individual probability. We're going to call it PI star, where star means nature or reality. So there's a true probability for individual I of a positive outcome. And so for all I, there's a PI star that's assigned to I by nature. And then if PI star is the probability assigned to I, then the actual outcome will be OI star, which is drawn from a Bernoulli distribution with probability PI star of positive outcome. So again, this star says this is the real outcome that happened. Now, there are two issues here. The first is whether these probabilities PI star actually exist. But there's another question, which is there really any uncertainty, or is everything that appears random to us really just a question of not having enough information or perhaps computing time to determine? So on these two issues, on the first one, we are going to assume that the PI stars actually exist. We don't exactly need them for our algorithms, and we can never get our hands on them, but we assume that they exist. On the other hand, we are agnostic as to whether the PI stars are always either 0 or 1, or whether they can have intermediate values. So whether there's really randomness or not, whether free will exists or not, we're completely agnostic. So, okay. There's a large statistic literature on the problem of forecasting, so weather forecasting, where on each day, the weather forecaster gives the probability of rain for tomorrow. On the next day, either it rains or it doesn't. We have a Boolean observed outcome, and that's what we record. And in the statistics literature, people look at infinite sequences of forecasts and observed behaviors. And one criterion that was proposed by Philip David in 1985 as a sort of sine qua non for forecasting is that the forecasts should be calibrated. So what that means is if we look at the support of the output space, and we look at every value V in that support, then if we look at the days for which the forecaster has predicted a V probability of rain, then in fact, on a V fraction of those days, it should have rained. Similarly for some other W. And if we look at all of the days for which W is forecast as the probability for rain, then in fact, on a W fraction of those days, it should have rained. Various strengthenings of calibration were considered. So for example, one might define many arbitrarily intersecting subsets of the days according to different types of admissibility criteria, and require that the forecasting algorithm be calibrated on all of these subsets simultaneously. So for example, we might require simultaneously that it should be calibrated on all even numbered days, or on all odd numbered days, and on all prime numbered days, and on all days after it has rained for exactly 40 preceding days and nights, and so on. And such algorithms have been constructed, and there's extensive debate as to their significance. Multi-calibration was introduced in the offline or batch setting in computer science by Aberd-Johnson, Kim, Reingold, and Rothblum, where the goal was to train a predictor based on samples from the joint distribution, again, individuals and outcomes, Boolean outcomes, so that the predictor is simultaneously approximately calibrated on all of a possibly large collection of large subsets. Again, with arbitrary intersections. So the seminal paper of Aberd-Johnson, Kim, Reingold, and Rothblum is the launchpad. It's the technical launchpad for the work that I'm going to be talking about in the rest of the lecture. So together with Kim, Reingold, Rothblum, and Gagliona, we have developed a new framework which we call outcome indistinguishability. And it is inspired from, by indistinguishability from complexity theory, as in the definition of pseudorandomness. So as you know, indistinguishability in complexity theory is always formalized with respect to a class of potential distinguishers. So for example, you might have all decision trees of height 6 or all polynomial size circuits or whatever, but you specify a class of distinguishers. And the requirement that we're going to be looking at is the following. As I said, stars always represent reality, and tildes for us are always going to represent things that have to do with our algorithm. So the algorithm that we want to build is called P tilde. And we would say that P tilde is C epsilon outcome indistinguishable, if and only if for every potential distinguisher A in our class C, the following two probabilities are within epsilon of each other. So they're drawn on the screen. On the left, we let the distinguisher operate on the data for the individual I, the prediction that is produced by the algorithm on individual I, and the true outcome that happened to individual I. On the right, we have, again, the individual I, the algorithm's prediction about I, and now, instead of reality, what we do is we draw from a Bernoulli random variable that has pi tilde as the probability of heads. And what we want is that no algorithm in our class should distinguish between these two distributions. And that's interesting. Something's just missing. Okay, so I should note that this probability can be estimated based on the training data. We never get our hands on pi star, but we do have training data of the form I and OI star. So we can certainly we certainly have these, and our probability space would then be over the randomness of A and the choice, the empirical distribution that we get from the training data. And of course, this we have no trouble with. Once we choose pi tilde, we can draw from it and find an OI tilde. Okay. Note that if non-extreme probabilities exist, we can never get our hands on pi star no matter what. Nature's probabilities are not available, but the definition doesn't ever require them. We never look at them in discussing outcome indistinguishability. So why this definition? We like to think of it in terms of the scientific method. So think about the predictor as a scientific theory whose predictions yield a generative model for outcomes. In other words, given individual I, the predictor hands us pi tilde, which we can then sample from. It's a generative model for OI tilde. So it's giving us some theory, some generative theory for the world. And if the class of distinguishers is the collection of all polynomial sized circuits, then the requirement says that the behaviors predicted by the theory cannot feasibly be distinguished from the behaviors on the real world, even when we're given access to the pi tildes. So in other words, if we were to satisfy outcome indistinguishability with respect to this class of distinguishers, there's no feasible way to falsify such a theory. And that is the scientific method. There's a beautiful YouTube video by Feynman talking about how science works. And he says, you know, we come up with hypotheses. That's our job. We're the physicists. Then we work through what are the consequences that we expect to observe given this theory. And then we go out and we look at the world and we see, did our theory predict well or not? You know, if what we see is contrary to what what our worked out consequences should be, then it's a bad theory and we have to reject it. But otherwise, it's good for now until we find something else that maybe shows us that we work out new consequences and then find out that one of those new consequences is falsified. Okay. So having framed these things in terms of indistinguishability, we can actually very naturally find ourselves defining a hierarchy. And the hierarchy, the levels of the hierarchy vary according to the degree of access that the distinguisher has to the predictor p tilde. So I just put a little reminder on the right-hand side to show you what's getting predicted from, what's getting compared to what. But here, when I describe things, I'm only describing the experiments on the right, not the one on the left with the stars. Okay. But it's really there, that's the comparison. So in no access outcome indistinguishability, the distinguisher only gets the description of the person and either the true outcome or a draw from according to the prediction, the sort of synthetic outcome. In sample access, that's the version that I gave before, we're giving to the distinguishers also the value that the predictor produced. Then the next level up is oracle access. So here we're going to let our distinguishing circuits have oracle gates where they can query the predictor on arbitrary inputs. Okay, so remember, we can't query nature on arbitrary inputs, but we can definitely query the predictor on arbitrary inputs. And then in code access OI, the distinguisher is also given arbitrary access to the actual program, the code itself, for the predictor. And the question that we study is it possible to construct OI predictors whose complexity, the complexity of the predictor itself, is independent of the complexity of P star, of reality, of nature's predictions? And in a nutshell, we find that the answer is yes for the two lower levels, the easier levels of the hierarchy, and it's impossible for the harder, more demanding levels of the hierarchy. And that's pretty interesting because it says that when you sort of see the whole result, it says that there are choices for nature that cannot be modeled simply. There's no simple algorithmic predictor that models them, even if all we care about is fooling some very, very simple distinguishers, but those distinguishers have oracle access to the predictor. So the first thing then that I'll tell the court is that having access to the predictor really matters. So what do I mean? What is the context for this? Well, just earlier this month, California Proposition 25 on the ballot, which was defeated, was actually a referendum on a law that had been passed and that replaced cash bail for certain kinds of charges with automatic risk assessment tools. Okay. And it required, the law said, gee, these things have to be audited for fairness every year. Well, divergence from reality is commonly viewed as unfairness. This is, an auditor that has oracle access, or for that matter, code access, even better, is sort of provably better able to detect unfairness of that type than an auditor given only sample access. Okay. So in a little more detail, and I'm going to actually sketch out some of these constructions, we get the following bounds. If our class of distinguishers are circuits of size S, or then there is a predictor whose size is on the order of S epsilon squared, that is C epsilon sample access OI. So that's the second level. If it satisfies this, it will automatically satisfy the lower level no access OI. And this is done by using, we can construct this by using a technique that was developed in the Hebert-Johnson, Kim, Reingold, and Rothblum paper that I mentioned before. It turns out that the lowest level of the hierarchy is essentially equivalent to what they call multi-accuracy. And the next level up is equivalent to multi-calibration, which I defined earlier. So, so that kind of takes care of the first two levels, and I will show you the modification of their technique that gives that bound. For the lower bound, we show that there exists an epsilon and a p star, and a set of size S circuits for which C epsilon oracle access OI requires predictors that are large. Their size is S to the omega of 1 over epsilon. And this is under an assumption about fine-grained complexity using a result of Goldreich and Rothblum, for example. There are other results that could also be used. Okay. So this is interesting. It's a scenario in which the complexity of the indistinguishable object does not scale nicely with the complexity of the distinguishers. And to our knowledge, this is unique in sort of the theory of indistinguishability. Okay. So, how do you achieve it? Great. So the algorithm for achieving it is, at any level of the hierarchy, is conceptually simple. It can be hard to do, but it's conceptually simple. So, and again, this is an extension of the technique that was introduced in HKRR. So first we initialize p tilde trivially, let's say, to be a half for everybody. And then we repeatedly search for a successful distinguisher A among our set C of distinguishers, looking for a statistical discrepancy between the predicted observations OI tilde and the real life actual observations or evidence OI star that we see in our training data. And of course, if the training set is large enough, these estimates will be relatively accurate. If a distinguishing A is found, then we nudge the values assigned to each individual in order to counteract the observed discrepancy delta A. And if necessary, that nudging will may require projecting onto the interval 0, 1. Okay. So we just repeat this until no remaining A in the collection is able to distinguish. And a standard potential function argument, such as the one that HKRR used in the multi-calibration paper, shows that there will be at most order 1 over epsilon squared iterations for this. Okay. Great. And again, we can estimate that probability from the training data. Okay. Now, it's not clear what the predictor looks like when you do this. So you can think of it as it builds a circuit that goes as follows. I've just kind of reproduced over here what the instructions are. So you lay down this circuit as you iterate during the main loop of the algorithm. You start with an individual I, you have code here for initializing pi tilde to be 0.5. Then you feed I and pi tilde to the to A sub 1, which is going to be the distinguisher that was identified in the first iteration. And in general, AJ is the distinguisher that's identified in the jth iteration. You need to plug in the code for nudging. So that means you need to have hardwired in the observed statistical discrepancy, because you're going to need that thing divided by 2, and you're going to need this difference that I have over here in the upper right hand corner, so you have a couple of copies of A to do that, and you carry out your nudge. And that gives you a new prediction, no longer a half presumably, for individual I, and you pass that down to the next distinguisher, or this component built on the second distinguisher that you found in your loop. So that's the whole procedure. And well, each of these, if we're looking at circuits of size S, each of these has size order S, and there are at most 1 over epsilon squared of them. And so that's that. Now, when we get to the oracle gates, things are a bit weirder. Like, we were talking about a distinguisher that has oracle access, but when we write down a circuit, we actually have to plug in the putative, the candidate predictor that it was having oracle access to. So in the first, the initialization stage, that plays no role. And if we think of this as sort of p tilde 0, the kind of dummy initialization, we're going to have up to, let's say that each distinguisher is allowed q queries, q less than or equal to s, of course, queries to the oracle. We're going to have maybe q copies of this for the q questions that it could ask about the initial distinguisher. That builds us a more complicated distinguisher. This one has size q, this had size sort of 1. Now, when we get to our second distinguisher, it has oracle queries to the thing that was created over here, or p tilde super 1, and it could have up to q of them. So I've got a whole bunch of copies of them, and so on. So the size now is growing by a factor of q at every step, and that's how we get s times q to the 1 over epsilon squared. So that construction works. And what the lower bound says is, you see how these things are growing really, really fast at each step. They're growing by a factor of q. What the lower bound says is that's unavoidable. There's nothing you can do about that, really. Okay. Now, what do we know about our predictor versus P-star, the truth? We've argued that a potential function argument says we need only 1 over epsilon squared iterations. So if we actually had, the full complement of updates, then the potential function would be driven down very small, and we would know we were very close. But we might have terminated without a full complement of updates. And so it may not be the case that P tilde is close to P star. It's true that none of the distinguishers succeeded, and that could be either, for example, because the collection of distinguishers is not sufficiently expressive, or maybe it's because the representation mapping suppressed crucial information that would be needed to separate out people. Okay. So when I talked about the scientific method and outcome indistinguishability, I sort of overstated the case a little bit. I said there was no feasible way to falsify such a theory. Well, it's true that with this representation of the instances, there's no feasible way to falsify the theory, but it might be feasible to go out and find a new way of representing people and bring in new representations of our people. So, and we're never going to know. We don't necessarily know this is the case unless someone walks out and finds a new representation and brings it. So we could sort of take a mistake-bound view of this. And this could be, let's say, the ultimate in socio-technical systems, where the socio part is the people who go out and find new representations, and the technical part is the one that builds the predictor from those representations and training data. So if a richer representation is found that permits falsification, we can say, hey, this is still a step on the path of progress. Let's define our new representation, let's say, to be the concatenation of the old one and the richer one. So now we have the stuff we had before and the new the stuff that somebody found. Let's define our new class C to be the old class C together with any new distinguishers that we want to define on the now new representations, this combination of old and richer. And let's go, run it through the crank, turn the crank. And what's interesting here is that this potential function argument applies. Any progress that you made in the past toward getting close to P star, you haven't lost, and you'll now be able to take more steps because you have you have information on which to do it. Good. All right. Now, there are many open problems and interesting research directions, and I'll mention a few of them in a moment. But before I do, I want to say a few words about a notion that initially I completely didn't understand, and I don't understand it yet, and it hasn't really been defined, but its importance is becoming increasingly evident to me. And that's what people call transparency. Now, again, it's really not well defined, but everybody talks about it. It's supposed to be the secret to everything, and tons and tons of articles about transparency. So here's my take on this. That transparency is sort of the glue that connects the technical to the socially acceptable. We've seen this even with, say, differential privacy and its use in federal statistical data. That I've talked to congressional staffers, and they say the Census Bureau did not make clear the method by which they were going to decide on the privacy parameter. Well, I don't know if they know it. I don't think they've decided on the privacy parameter, but they wanted that kind of transparency. How did you decide, or how are you going to decide exactly what you're going to do? Now, I have been working with Martha Minow in the law school on questions of trust and distrust of technology. And one thing that comes up over and over again is that people don't like AI, they don't trust AI. And one of the reasons they don't trust it is because they can't understand what are the algorithms doing. So if you think of like a generic neural net as sort of in training, learning a collection of features which then get combined via logistic regression, the features that are learned are not intuitive. People can't see themselves in the features. They don't understand why this weird thing that you've computed from them is at all relevant and should be considered by anybody for anything. So distinguishers, though, I think, so in some sense, transparency, well, if you could sort of explain what the features meant, people would be maybe more comfortable. Whether they should be or not is another story, but they might be more comfortable. I suspect that the same thing does not apply to distinguishers. So if you think of distinguishers, if you say, well, we start off with some initial value and we use wacky functions to try to see whether we can distinguish the fantasy world of our candidate predictor from the real world. And if some wacky function makes this distinction, then we make adjustments. Somehow the distinguishers aren't about the individuals. They don't feel like they're about the individuals. And it struck me while preparing this talk that perhaps this sort of shift to this distinguishing approach might help make AI more transparent and more acceptable. But this is just something for like thought, food for thought. Another aspect of transparency is that transparency in the real world is resisted very heavily on the part of firms because of on the grounds that software is proprietary. And somehow the separation between the lower two levels and the upper two levels of the hierarchy show that there really are solid mathematical grounds for demanding access. And that also that Oracle access on its own can be very powerful and perhaps sidestep the proprietary issue. Okay. So a few directions for future work. What the elephant in the room with all of this is that the class C can be very, very large. And when looked at in the right way, previous work, 2 papers, Kearns, Neal, Roth, and Wu, and also HKRR, connect the difficulty of finding a distinguisher that is succeeding with an agnostic learning problem. So we have to deal with that fact. Now, one philosophy that one could take is the one that Neal, Roth, and Wu, I got it wrong. Okay, Neal, Roth, and Wu use, no, that's right. In differential privacy, and Kearns, Neal, Roth, and Wu use in fair learning. And it's to say, well, so what? I don't care that this thing reduces to an agnostic learning problem, and agnostic learning is hard. We have all sorts of heuristics, and they behave very, very, very well. And sort of as long as everything that we're doing with the outcomes is really kosher, this is fine. So this is certainly one approach, and it may be an excellent one. Another approach that I want to look into is something that we used in some work on the complexity of differential privacy, where we're trying to find let's say a small database that can handle many, many queries. And that is basically that it may be that if you appease a collection, a small random collection of sets, subset, so a subset of C that's small and contains some random elements of C, then maybe it's likely to be very useful in terms of satisfying most of the distinguishers in the collection. So this is a direction that I think could be fruitful, as it was very fruitful in the past. Another direction is to look at outcome indistinguishability for arbitrary valued outcomes, not just Boolean outcomes. And some work that is definitely related to this in spirit is the very recent moment multi-calibration work of Young Lee, Pai, Roth, and Vora, which calibrates moments as well as, yeah, okay. Another direction is to go back to the world that the statisticians were looking at, the forecasting online world, either in the distributional or in their case, it was non-distributional case. And so look at online outcome indistinguishability. So we know we have some impossibility results and maybe we think some things are possible. So the question there becomes, what's the most general class of distinguishers against which outcome indistinguishability is possible? And finally, no amount of work can ever compensate for lousy data. And in her gripping book, Automating Inequality, Virginia Eubanks gives excellent examples, especially in chapter 4 of the book, on other ways in which unfairness is introduced into algorithms. In particular, she's discussing in the case of Child Protective Services that's making decisions about whether to remove a child from the home. So definitely life-altering consequences. And she discusses how the meanings of certain variables are completely different for poor people and wealthy people. So the state has no information, for example, on drug treatment programs for wealthy people who went to private clinics. They have lots of information about the use of these programs from poor people who use state funded programs. So the very meaning of, gee, no record of alcohol abuse in the house is completely different in these two populations. She also talks about how the outcome proxies, the things that you use to label your training data, can be very different in different populations. And no amount of, playing with lousy data is going to compensate for that. So the problem then is, what automated tools can we come up with? What can we do to, in a rigorous way, interrogate whether this is these kinds of discrepancies are going on in the way we are representing individuals and in the proxies that we use for our labels for training. Okay. And finally, turning the tables, if you go to this website, it gives you a scoring function. So they did a study of how do you predict whether or not a judge is going to fail to adhere, meaning detain somebody for more than 48 hours on unaffordable bail without due process of law. So they built a simple device for predicting, given a few properties of the judge, what is the probability that the judge is going to violate due process of law. And with that, I'll take your questions.
Thank you so much, Cynthia. I guess I have my mic on, so I can clap. All the other people are clapping, and I'm happy to moderate questions. You can, I guess, raise your hand or type something in the chat or unmute your mic and just probably start speaking, because so far not so many people are speaking that would cause any problems. But I guess Salil has his hand up, so let's start with Salil.
Hi, Cynthia. Thanks for the really thought-provoking talk. I have a question about the interpretation of the negative result about the Oracle OI. So you interpreted, or from that kind of, it went to sort of advocating that we should, using it as a reason to allow access to the prediction algorithms or access to the code. Partly playing devil's advocate, a different perspective could be maybe the result is saying that makes fairness too hard, and what we should do is agree on our class of distinguishers ahead of time, not allow them to be dependent on the predictor, and if we satisfy indistinguishability for those, we should be happy. So I was wondering if you could sort of reflect on that.
No, I mean, the reason I can't is I definitely understand your point of view. I think that, you know, I think that if having this tool lets us uncover ways in which the device is unfair, meaning that it's departing from reality, we have the option then of deciding what to do with that information. But I don't think we should preclude it in the first place.
Thanks.
Okay. Hi, Richard.
Yeah, Richard.
Hi, Cynthia. Thank you for the talk. I have a question about the sample OI section where we did the construction using nudging algorithms.
Mm-hmm.
How do we find these algorithms to nudge with? And does it contribute to like we talked about earlier how like AI has features that are hard to understand.
Good. So we have specified our class of distinguishers, and exactly this complexity problem that I mentioned, the hardness of agnostic learning, says that we don't have a way that provably efficiently finds a successful distinguisher if a successful distinguisher in fact exists, if there is one that could pick up a discrepancy between the predicted outcomes and reality. And so that's what the first bullet in the open problems, future directions, is talking about. As for the code for the nudging, it's very, very simple. Let me see. Oh, come on, talk to me. So we can estimate this probability over an I chosen from the empirical distribution. We can estimate this probability, we can get this probability. We can tell whether that difference in absolute value is large enough to trigger a change. And if so, then we look at that distinguisher. For individual I, we look at the behavior of that distinguisher on individual I with pi tilde and 1 minus what happens with individual I with pi tilde and 0. That's an easily computed quantity. And then we multiply these together, divide by 2, and project onto 0, 1. So that's how we do the update for individual I. So the nudging is simple. But finding finding an A that we need to update, that's the hard problem. And I should also note that there may be many of them, and the predictor that you get will vary according to which ones you choose for your updates. But if you do enough updates, you'll get close to the same place, to P star.
Madhu.
Hey, Cynthia. Question about this notion of representation. You said it's very important. Can you give us some anecdotal examples of how the choice of representations made a difference in our ability to predict? Maybe either in this physics context, which is where you first raised the possibility, but also in maybe social context, if that's easier to come up with.
So you're asking whether, I'm sorry, if I have a representation where it mattered in credit?
No, there was this notion that there's a loop where we pick a representation for our individuals.
Yes.
And then when we add more features or something, then maybe our classifiers can get better, right?
Right. So if you looked at, let's say with the tumor example, if you look at different studies that study different groups, and then you say, okay, and these are giving you different numbers, different studies that are looking at different parts of the genome. And then you say, okay, let's find a representation. Let's represent people now by the union of these things. And let's go get some data and see what we find. So that would be an example, if I understood your question correctly.
So there is a comment in the early chat part that I thought maybe I should ask your reaction to from Phil Milzo, that this is very reminiscent of generative adversarial networks.
I'm sorry, say that? I didn't hear the beginning.
That what you're doing is reminiscent of GANs, generative adversarial networks. Would you be willing to comment on the connection or like thereof?
You know, it's a very interesting connection, and it may be that you want to use GANs to help you identify these distinguishers. We're certainly starting to think about these things. We think there's a strong connection. Yes. Essentially, you're trying to find ways of generating samples. And so, yes, we think it's a strong connection, and we're excited to look at it. We were talking about it just this morning. Okay.
Thank you. Any last minute other people who want to ask questions?
I have a quick question. Do you have, Professor Jork, do you have any comments about kind of including proxy variables where maybe sort of some kind of fairness issue is caused by, like, the only thing I can measure is not a good way to access what I really care about. Like, all I have is some event in the next few months, and if that can be added to the outcome indistinguishably. Anyway.
Yeah.
Thank you.
So that was my last open question was actually, are there ways of evaluating the attributes that you use for representing individuals and for the outcome proxy. So a typical example is you're trying, I'll say not the one that everybody has heard of, so that those of you who, some of you don't know this one. Okay, so you're trying to figure out whether the child is actually going to be harmed. Instead, you use whether there was a second call made to Child Protective Services, which does not mean the child was harmed. It means maybe the neighbor doesn't like you, or maybe the neighbor heard some yelling and didn't like it or whatever. I mean, maybe justifiably didn't like it, but in any case, it doesn't mean the child was harmed. But the second call is used as a proxy for a positive outcome.
So I saw that Andrea Lincoln had
find these. Yeah, go ahead, Ava.
Andrea Lincoln had her hand up. I'm happy to listen to the question. I also want to point out to the about 100 other people that my screen is showing about a third of the people here. So this person was lucky because that was on the front screen. But I suggest you use the button on the bottom to raise your hand instead, and because that way I definitely see it. But meanwhile, Andrea can answer your question.
You mentioned that there's a fine-grained complexity assumption that ends up showing this result? Which assumption is it?
This is
Uh,
an assumption about the hardness of counting K-cliques.
Thank you.
There is a new question in the chat window that I'm happy to read. There is also a sense that features used for classification tasks should be related, appropriate to the task. So do you view using AX in the predictor as another feature, or do you view it as appropriateness to be used for the task?
Give me a moment. Let me reread that because it's
Yeah.
the hard question. There's also a sense that the feature. Right. So do I view using A of X in the predictor as another feature? I hadn't thought of it that way. So you're asking whether I view what the distinguisher does on this instance as a feature?
Yeah. Because that is being used in the code for the final prediction.
Mm-hmm. And do you see it as problematic, Sumekha?
Yeah, in the sense that like if we think of thinking of like multi-calibration, then if one of the if multi-calibration, it started with like the groups, the calibration groups were like say based on gender or someone, then basically the predictor is actually using the gender of the individual to in their prediction algorithm.
I don't view that as problematic at all.
Okay.
It's legally problematic in some cases. And if it's going to be used by government, you'll definitely be subject to strict scrutiny if you decide you want to use sex as an attribute. It's not even clear that you're allowed to measure whether your algorithm is fair or gender balanced. It's an incredible mess, but I don't view it as problematic from a fairness perspective to use the attributes. And I think that, and I know John Kleinberg was here, and John has a paper together with Sendhil Moinathan about essentially why you really want to use as much of the information as you have, that you will be more fair.
So John is still here if he wants to comment, but I think your own example, Cynthia, had this, right? You were talking about how certain attributes have different meanings in different communities.
Yes.
And if we're not allowed to use the community belonging, then I guess we're mixing up these meanings, which is basically the reason you might want to use them.
Yes. And in our first paper on fairness through awareness there referred in part to understanding basically the cultural differences and the differences in the data of exactly this kind of thing, although it was said much better and with much more clarity by Virginia Eubanks and others since then. Yeah, thank you.
Okay, thank you.
Yeah. I'm reading Paul's question. Is there a way to use this to tell that the current representations are particularly bad? All the time in the history of science. Oh, okay, just answered. Okay, good.
Yeah, he felt like you already answered it.
Okay.
Well, I guess, thank you very much, Cynthia. This was a really enlightening talk with both technically and for its relevance for society. And you did exactly what I claimed you're always doing, using our tools and techniques to shed light on societal issues, which I truly appreciate. Thank you very much. And I guess people can either unmute and clap, or I guess put up their clapping hands.
Thank you, everybody. Thank you. Thank you.